Okay, so as we look at section 3.3, and you can see it's titled One-Sided Limits, we need to start looking at how we take the limit of functions, but just from what we call the left or from the right. So the first thing we have is this notation here that really gives us an idea of, how we write this kind of thing. So when you see the limit as x approaches a number, let's just use 4, but you see a little superscript up there that looks like a negative sign, that would mean that we're coming in from the left. So that would mean that we're using values a little lower than 4. So 3.9, 3.99, and so on. And then when you see limit as x approaches 4 from the right, you'll see a little plus sign up in the superscript there. And that would mean that we're using something like 4.001. Numbers a little bit bigger than 4. So without working with numbers just yet, let's just look at this graph I have here. So you'll notice that at -4, there's this split, and there's two functions, one coming in from the left, one coming in from the right. So we learned in our last lesson that the limit, in this case, as x approaches -4 of this function, would not exist. But we're going to look today a little bit more at why that is. And the reason was because these functions did not approach the same value from the left and the right. So you can see the picture down here, right? If we take the limit as x approaches -4 from the left, it looks like we're approaching -4. But if we so we don't pay any attention to any function coming in from the right. But then if we switch gears and we say let's approach -4 from the right hand side, we don't look at anything from the left. And here, I would say it looks like we're approaching 3. And since these y values are not the same, that's why the limit overall didn't exist. So on the bottom of this page here, we're just kind of reminding ourselves that in order for a limit to exist, basically the limit as x approaches a number from the left must equal the limit as x approaches the number from the right. So just something to keep in mind there. So let's look at another example. In this case, they're giving you the function, but they're also giving you the graph as well. And it would be helpful to have either, really. So when you ask to find the limit as x approaches 1 from the left, then that means I'm only looking here, what y value does that thing approach? And it looks like here the answer is -1. You could have just as easily taken that 1 and replaced it into this top function, because this domain right here tells me that's where I'm using values that are less than 1. Then we switch gears, we go the limit as x approaches 1 from the right, and in this case it looks like 2. And so then we still want to remind ourselves of the overall conclusion, right? If one had asked me, find the limit as x approaches 1 in general, in this case I'd have to say doesn't exist, because these two guys are not the same. So why don't you pause the video and try example 2, same idea, and see if you can kind of get those 4 questions. Okay, so the first part says, let's take a look at the limit as x approaches -2 from the left. Well, here's the problem. I don't see anything over here coming in from the left. So that answer would also have to be doesn't exist. Then it says, let's go limit as x approaches -2 from the right. Well, that one I see, that looks like it's heading towards 2. But again, because these two are not the same, this answer has to be does not exist. Now, let's take a look at the last question, which is just f of -2. Let's separate that a little bit. What we have to understand here is this is not the same question, really. F of -2 is not really interested in whether I'm approaching a number. It's really asking what is the exact value when x equals -2. And in this case, the answer would be 2. Now what we would look for here is like open circles versus closed circles. So like for instance, if we were looking here at x equals 3, right, f of 3 would not be 0, it would be -3 because of this filled in circle down here. So these are just things to be aware of as we continue on. All right, example 3, I'm going to take away the graph here and just say, what if we gave you a function? Well, the idea here is still the same as we were talking about in the last lesson. So if you ask me to evaluate this function and do the limit as x approaches 2 from the left, technically, I'm really not supposed to be plugging in 2. I'm supposed to be substituting like something a little lower, so like 1.999. So if we had a calculator, obviously that would make that a little easier. But what you wind up seeing is you're doing 4 minus something that's really, really close to 4. Let's call it 3.9999, right? And so that gives me an answer that's really, really tiny, something like that maybe. But what we learned last week is, for all intents and purposes, why wouldn't we just take the 2, plug it in, and get an answer? And that's exactly what you should do. So our conclusion here is 0. So a lot of people ask, well then why would you show it like this? Well, here's why. Look at example 3c. If you were to plug in a number a little bit higher than 7, so let's say the square root of 7 minus 7.001. The problem here is you would get a negative 0.001. And as we know, you cannot take the square root of a negative, so this limit would not exist. But what we have to be kind of understanding here is that if you ask me to approach 7 from the left, then I could do it, because 7 minus 6.999, for instance, is something that you can take the square root of. And still it's very tiny, and so this would allow us to conclude 0, right? Because the square root of something really, really tiny is just about something really, really tiny. And so we just have to be aware in situations like letter C that, yes, we're plugging in, but there's much more behind the scenes. There's a theory behind it, there's a concept behind it, and there's a reason for why we're looking at it from one side or the other. So try B and D on your own, and we can always talk about it at some point in class if you have any questions. So we move on to this idea of continuity, right? And we have 3 checkpoints that we have to make sure we test to see if a function is continuous. And the first one is that you have to be able to look at a graph or look at an equation, plug in a number, right, and actually see the value. Have to get that y value. And the second condition, says something that we've been playing with all along now here for the last week or so, and that is that the limit must exist. That's really what that's saying. And in order for a limit to exist, the limit from the left has to equal the limit from the right. And then the last one basically takes number 1 and 2 and says they have to be the same. So take a look at this picture, right? At point A, right, we're looking for which condition, which one of these Roman numerals here is not met. Well, at point A, it would be Roman numeral 1, because why is there an open circle here, right? At point B, the limit does exist. Looks like it could be 2 or something like that. But this idea that the value of whatever that number is, f of that number, isn't the same, right, as this dot, well, that means Roman numeral 3 is not being met, right? The limit has to equal the actual value of the function. And then if you jet all the way out to point C, those things aren't even approaching the same number, so the limit doesn't even exist. So Roman numeral 2 is not being met. So again, what are we talking about? For me to deem a function continuous, I have to be able to say these 3 things. Okay, let's look at an example. So we're going to try and prove if this function is continuous. Well, the biggest concern here is that this equation was split at 3. So I really, really need to check what's going on at x equals 3, right? So what I'm going to do is I'm going to first and foremost say, what is f of 3? And guess what? Right away, you don't have a place to plug that in, because they haven't said so in the domain. So f of 3 doesn't exist, so it's not continuous. Now, let's look. That was almost too easy, right? So let's look a little further and just kind of dig a little deeper. Let's just for a minute, we're going to change this problem up. Let's add an equal sign right in here on the bottom one. So now that's where you can plug in 3. So that would mean that f of 3 is now equal to 3 plus 2, or 5. Okay, so Roman numeral 1 from our conditions was met. Now, Roman numeral 2 is a little bit more involved. It says you got to prove that there's a limit from both sides, so let's do that. We're going to do the limit as x approaches 3 from the left, and if I say, well, which one do I pick? Look carefully. 3 from the left would mean numbers below 3, so that would be the top piece right there. So I'm going to plug 3 in there, and I get 5. Then I'm going to take the limit as x approaches 3 from the right. This would be the bottom function. So that would be just x plus 2, and that also equals 5. So Roman numeral 2, the limit exists. And then finally, Roman numeral 3 says that these values, right, got to be the same, and they are. So I'm good here, right? The limit as x approaches 3 does equal f of 3, and that equals 5. So then in a case like that, I could say that the function is continuous. So a little twist on example 4, but that's the kind of thing we're looking for. Let's try another one. Okay, in example 5, really this is a different kind of example because there's really not much work to do, and here's why. You were looking at a polynomial, and so if you remember from some of our earlier conversations about some of the review things, polynomials have a domain of all real numbers, right? And that means that there's never a place where there's a restricted value, you can't divide by 0, something like that. So this is continuous everywhere. And that is true of every polynomial that you run into. Any polynomial you see is continuous everywhere. Okay? Same thing with something like example 6. Example 6 is exponential. Remember we talked about those kinds of curves, right? Well, if you remember the way those look, they kind of just look like this, right? There's no break there. There's no hole, no asymptote. So exponential are also continuous everywhere. But then you get to something like example 7, and it says determine whether this is continuous, and red flags should go off. X cannot equal -4 here. So it's not continuous at -4 because you'd be dividing by 0. We can't have that. So what we're seeing on this page is the idea that there are some key connections to things that we've talked about in the past, and we want to look for those. So we've seen 4 different kinds of functions if you think about it. We looked at a piecewise function, and we learned that if we're going to determine where that thing is continuous, we have to really look at the break, the break in the pieces. Then we looked at polynomials, exponentials, rational functions in example 7, and they all have very specific things we're looking for. So why don't you try this last page here, and then we'll kind of talk about in class where we need to look, what your misconceptions might be, and some of the things that you might be thinking based on what you saw in this video. So I hope this helps, and come in on next time with any questions you have.